Okay, now I'm going to do this for Neptune. And again, I'm going to wait until Neptune is at the corner of my little box here to use that. That's probably close enough there. So this is February 2035. I actually don't need the month there. 2035 will be just fine, and then I wait for Neptune's one orbit. Of course, it doesn't matter when I actually measure it. The orbital period and the distance are the same. So my starting date and finish date could be any time. Okay, here we go, almost there. I actually don't see Neptune very well here. That's good enough, 2298. And now I'm going to look up the data for these. So here's Saturn 9.03 AU. And let's see if that is the correct one. Okay, actually not, 9.586 AU. I'm going to write that down. What it gives up here is the current distance from the Sun, whatever date we're on here. That's like in the year 2298. Well, this one here is the semi-major axis. That's the average distance. That's the one I need, 9.586. For Neptune, that number comes out to, there it is, 30.001 AU. So those are numbers I'm going to use. Okay, back to this one here. So that would be Saturn and what did I say here? Neptune. And for Saturn, I had a distance of 9.586 AU, and for Neptune that was a distance of 30.001 AU, and then for Saturn between November 43 and April 73, so really close to 30 years, 29 years and 5 months. 5 divided by 12 is about 0.4, so let's make it 29.4 years. And for Neptune between 2135 and 2298, so 163 years. Okay, and then for Pluto, I just give these away without measuring them. So for Pluto, that is 247.85 and 39.357. As you know, Pluto's no longer a planet, so I like to include it here, but I make it optional. If somebody says, oh no, it's not a planet, exclude it. If you say, oh no, let's give it a planet, include it. Anyway, let me show you the calculations here. You can see that here on the lab sheet itself. I did the first one here for Mercury. I did this one here actually for the moon Io of Jupiter, and then the third one is for, I believe, a moon of Uranus, and so I'll show you the calculations here for a couple of the planets. Move this one over here, move that one over there. There we go, and I'm gonna type in the numbers hopefully. Okay, I'm not gonna do Mercury again because you can see that in your lab sheet. I'm not gonna do Earth because that's trivial, so let me do Jupiter and Mars as examples. So Jupiter would be 11.86 squared. That's what it says here, p squared. So here's the period p, 11.86 squared. Divide by a cubed, so the distance a, 5.203 cubed, and I hit enter and I come up with 0.99, rounded 0.999. And now I'm going to do Mars, 1.86 squared divided by 1.52 cubed, and I come up with 0.985, and that's what I'm going to write down, 0.985. and then I'll let you calculate the other 3 or 4 planets. The gist of the story is that when you calculate this one here for each planet, you come up with virtually the same constant, 1.002, 1.000, 0.985. You know, when you round that, it's really close. And that's what Kepler's third law says, that when you compare the planets, they obey this kind of relationship. Why is it not exactly 1.00 and so on? Well, here, that's a rounding thing. I only gave it 3 significant figures, so if this is not exactly 0.241 but 0.2406 rounded or something, which I don't know, then the last digit here cannot be absolutely accurate. Same thing happens here, same thing happens here. Here I know why this one is so far is a little bit more off, and that is because the actual period is 1.88 years rather than the 1.86 years, and so I must have measured there just slightly off. But you watched me how I measure it, and so you can kind of figure, oh yeah, it's a little bit off, and that's why the constant here at the end is a little bit off. Okay, I'm gonna take this off here. Don't need it anymore, and let's move on to Jupiter's moons. So I'm gonna do basically the same thing that I did a moment ago, but you guys have to pay a little bit closer attention to here, because a moment ago I wrote down the numbers, but now you guys have to look at that. I already gave away the distance, and I put that in the radius of the planet. That means that if you take the radius of Jupiter and you go 6 times out, that's where Io is. You go 9 times out, that's where Europa is. Ganymede 15 times out, close to 26 times out. When you do the calculation, you will use the 26.3 and the 5.91 and so on. Okay, so let's go to the software and look at Jupiter's moons. First, I'm gonna change my location back to Earth. There we go. I got an overkill of stuff on here. I don't need the planet orbits anymore. I don't actually need the planet labels anymore. I'm gonna get the moons specifically for Jupiter, and they're all there. I'm gonna label them. I'm gonna put the orbits here. Okay. Okay, now I'm gonna look at Jupiter. There it is, and I'm gonna zoom in a certain amount. Let's see if this works. Okay. Okay, actually I don't want to have the orbits. That's an overkill. Get rid of those. And I'm gonna turn this one here to use, this one is probably working. Okay, that should be good enough. And what did I want to do? Oh yeah, I want to get rid of this one here, and I have to drastically change my units. I'm gonna make this to 10th of a day, and let's start at a convenient time and date. So let's make it 1st January, and let's make it a recent year here, 2011 for example. Okay, I will change one more thing, and that is actually change my base plane to ecliptic plane. That's better, looks better. Okay, I'm about ready to go here. Okay, I'm choosing, so I'm going to look at Io, Europa, Callisto, and Ganymede, and I'm going to look at Io first and go forward in time, one step at a time. Notice that Io goes in front of Jupiter. Oh, I forgot one little thing. I should start this at a convenient time as well, so I'm just going to make it 1 minute after midnight. There we go. Oh yeah, I guess that changes it a whole lot. So Io will stay right there. We'll have to return to right there.